All right, so we're starting section 3.3, and this first video is going to cover the concepts, and then the following videos will be examples. So the concepts for this section are increasing, decreasing functions and the first derivative test. And we're familiar with increasing and decreasing functions. So I drew a picture. Here's this green curve. It's an increasing function, meaning it's going up. You're supposed to read these graphs from left to right. So if I read this thing from left to right, it's going up. And so another way of saying that, f of x is increasing when x1 is less than x2. So x1 is the left value, x2 is the right value. And f of x1 is less than f of x2. So the y-coordinate for the first point is less than the y-coordinate for the second point. All right, and that occurs for every point on this graph. Now decreasing, so we have x1 less than x2, left point, and then right point, and the left point, f of x1, so that has a y-coordinate that's bigger than the y-coordinate, which is f of x2 of the second point. Or you could look at it as the second point's y-coordinate, f of x2 is less than the first point's y-coordinate. So so for decreasing, it goes f of x1 less than f of x2, or just writing it so that it stays as a less than sign. It's the y-coordinate of the second point less than the y-coordinate of the first point. All right, so that decreasing function, reading it from left to right, it's going down. Then there's constant function. And constant function is just a horizontal line. And so the y-coordinates f of x1 and f of x2 are equal to each other because they're all on the same horizontal, or on the horizontal line. All right, that is the definitions for increasing, decreasing, and constant. Now there's a way that you can tell that a function is going to be increasing, decreasing, or constant by finding its derivative. And this is theorem 3.5 in the textbook. And so you have a function is continuous on the closed interval, it's differentiable in the open interval AB, and like in the previous videos where I talked about differentiable, that means its derivative exists on the entire open interval AB. So you got to have it be continuous and then differentiable. So if its first derivative, f prime of x, is greater than 0, so if its first derivative is positive for all x in the open interval AB, then f of x is increasing. All right, so as long as its first derivative is positive, it's increasing. The second thing is if the first derivative is negative, so if that's less than 0 for all x, then it's decreasing. And then if its first derivative is equal to 0 for all x, then it's constant. All right, so if it's positive first derivative, it's an increasing function. If it's negative first derivative, then that's decreasing. And then if its first derivative is equal to 0, then the function's constant. And so I drew a picture, and here you have the first portion is decreasing. And I drew a yellow horizontal line to signify that it switches from increasing to constant. And for the left portion, to the left of that yellow dashed line, so it's decreasing, that means its derivative f prime of x is less than 0. Then in the middle, I have constant, and that's a horizontal line, so its first derivative is equal to 0. And then on the rightmost portion, I have an orange is f prime of x is greater than 0, and that's decreasing. So again, negative derivative, decreasing, derivatives equal to 0, it's constant, positive first derivative, it's increasing. So that's a way you can tell where the graph's going to be increasing, decreasing, or constant. Which leads me to the first derivative test. So the first derivative test says let C be a critical number of f of x, where f of x is continuous on an open interval ab, I equals ab. All right, so this just requires the function to be continuous on an open interval. So from section 3.1, we talked about critical numbers. So we're going to have to find a critical number. Now, if on that same open interval for which the function is continuous, if it's also differentiable on that interval, except possibly at the critical number c, because recall that a critical number means the first derivative is equal to 0 or it doesn't exist at c. So the whole function needs to be differentiable on the interval except possibly at c, just based on the definition of critical number. So it might not be, its derivative might not exist at c. All right, most of the time it's going to be equal to 0. Then the point c comma f of c can be classified as follows. All right, so you have a critical number, the function is continuous, it's differentiable, it might not be differentiable at c, but at that point, c comma f of c, it can follow into three conditions, three scenarios. And the first scenario says if its derivative changes from negative to positive at c, then that point, c comma f of c, is a relative minimum. The second, so that's going to be, so it either changes from negative to positive at c, relative min. Or if its first derivative changes from positive to negative at c, then that point is a relative max. Or if the first derivative doesn't change signs, then f of c comma f of c is neither a relative max or relative min. All right, so I tried to underline the key words here for the first derivative test. So first derivative changes from negative to positive, then that means it's a relative min. And from negative, right, that means its first derivative is less than 0, so that means the function's decreasing. And then if its first derivative is positive, that means the function is increasing. All right, so another way of stating it is if the function f of x changes from decreasing to increasing at c, then it's a relative min. Same thing as saying this first derivative changing from negative to positive. All right, and so for here, for the second one, changes from positive to negative for its first derivative. We know for the first derivative to be positive, that means the function's increasing. So when it's negative, that means the function's decreasing. So you can think of it as f of x changes from an increasing to a decreasing function at c, then that point's a relative max. Okay, so here's a picture. The one on the left represents a relative min, and we have this open interval AB. And in this case, it's a relative min because on here C, to the left of C, you have the functions decreasing, and that means its first derivative is negative, all right, or less than 0. Then to the right of C, the first derivative is positive. So it's an increasing function to the right of C. So it switches from negative to positive based on its first derivative at C, or you can think of it like switches from decreasing to increasing. All right, so that point is a relative min. Here's a picture representing relative max. And to the left of C, the graph is increasing, which is the first derivative is positive, greater than 0. And then to the right of C, its derivative is negative, or the graph is decreasing. All right, so it goes from increasing to decreasing at C, positive to negative for the derivatives. And then here's a picture that represents neither. So you have C, and to the left of C, the function is increasing, and its first derivative is positive. But also to the right of c, the function is still increasing. And again, it's positive for its first derivative. So the sign doesn't change for its first derivative. It's positive on both sides. So this is a case where it's neither a relative min or a relative max. I believe they call this, which we'll learn in next section, is called a inflection point. All right, so that's the concepts. The next couple videos are going to be examples where we apply the first derivative test to find this point, f of c, and determine whether it's relative min or relative max, and that depends on if the sign for the first derivative changes from positive to negative, or opposite, negative to positive. All right, so that's it for this video. Next video, go into examples.